So chapter 20 also has this interesting section on the chemistry of nitriles. And you might be thinking this is an odd thing to be in the chapter with carboxylic acids, because a nitrile is an organic cyanide. So RCN. Cyanide itself is the CN minus anion. That's a cyanide. So sodium cyanide, for instance, is NaCN. An organic cyanide, RCN, is called a nitrile. So why on earth is this in the chapter with carboxylic acids? Well, they don't look a whole lot alike at first glance, but if you look at it, they do have the same oxidation state. We have a carbon with 3 bonds to it, to a heteroatom, to an N or an O, right? There are no H's on the carbon in either case. There is a pi bond to the carbon, so in both cases. So there's actually more similarities there than you would think, and that shows itself in similarities in reactivity as well. Maybe not as much with carboxylic acids, but similarities with carbonyl compounds in general. So let's look at 2 ways that we can fairly simply produce a nitrile. The first way is going to take advantage of the fact that the cyanide ion is an excellent nucleophile. This minus charge right there is very effective at attacking electrophilic atoms, so we can do an SN2 reaction. The cyanide ion is a perfect nucleophile for an SN2 reaction. Sodium cyanide, remember we said, is CN minus. The cyanide ion can attack this carbon that has the leaving group on it. That'll head out, and we'll do an SN2 reaction to produce this nitrile right here. This really only works on primary or secondary alkyl halides or alkyl tosylates, something with a good leaving group. You can't do an SN2 reaction on a tertiary carbon. There's too much steric hindrance there. So one really nice way of making a nitrile. Also interesting because this right here is a new carbon-carbon bond, which we can take advantage of in our reactions of nitriles here in just a second, but really simple way of producing a carbon-carbon bond. Another way of making nitriles is by dehydrating amides. So in our next chapter, when we're talking about carboxylic acid derivatives, we're at C double bond O and then something else out over here. An amide, like this one, C double bond O N, with H's or R's attached to it, that's an amide. Amides can be dehydrated to produce nitriles. So what do we mean when we say dehydrated? Well, if we look at this O, look at those 2 H's there, if we were able to remove essentially minus H2O, I'm going to put that in quotes because that's not what actually happens, but that's the overall net effect of dehydrating an amide. We end up with a nitrile. The reagent that we use for that is SOCl2 thionyl chloride. You may remember thionyl chloride from chapter 17. Thionyl chloride reacts with alcohols to turn them into alkyl chlorides. It works as a dehydrating agent in this case, but the overall mechanism is very similar. What happens, here's thionyl chloride, that gets attached to the oxygen, and what can happen then, the water or a conjugate or some other base that's present can get rid of one of these H's from the amide. Then when the base removes the second H from that amide, that forms the triple bond, and that kicks out this whole thing over here. Notice we make a SO double bond, kicks out a chlorine. we get SO2 as a product. We end up with actually 2 molecules of HCl produced, so sometimes there's another weak base that's put in to capture that HCl that's produced as a result. So interesting reaction, but very similar to a mechanism we saw in chapter 17, ROH converted to RCl. That's with this exact reagent here. Also, POCl3, ROH, POCl3 makes it into an alkene. You'll notice that's also a dehydration, just like this is a dehydration, essentially. So POCl3 also works for this reaction. So not you will not be asked to draw this mechanism. It is still nice, I guess, to be able to understand where this comes from. I think anytime you can have some sort of understanding of the mechanism of a reaction, that helps you remember the reagents a little better. So understanding that both SOCl2 and POCl3 will attach to an oxygen, making it into a better leaving group. So once we have a nitrile, let's look at what we can do with it. Just like a carbonyl, the nitrile carbon is electrophilic. So we've seen this reaction several times in our ketones and aldehydes chapter, where a nucleophile adds to the carbonyl carbon, kicking the pi electrons up onto the oxygen. That's because this carbon has a partial positive charge, both inductively from that oxygen and due to the resonance structure, the secondary resonance structure that we could draw for that. A nitrile behaves similarly. Inductively, the N withdraws electron density from that carbon, making the carbon electrophilic, so a nucleophile can attack it. The only difference here, I guess, is that we have N instead of O, and that because we started with a double bond, we made a single bond here, but the nitrile has a triple bond, so one addition of a nucleophile makes it into a double bond. There are cases where we can add nucleophiles twice then to that. We'll see how that works here in just a second. Nitriles are very useful synthetically. They can be transformed into lots of different things. Amines, carboxylic acids, or ketones. Those are the most common interesting things we can do with a nitrile once we've created it. In each case, we have a nucleophile has attacked the nitrile carbon. So the way that works here, let's look at lithium aluminum hydride, a reducing agent. It reduces carbonyl compounds to alcohols. That's because it behaves as if it is H minus. We'll draw the mechanism here in a second, but we're able to actually add 2 of them to the carbonyl carbon, reducing the triple bond to a single bond. The Grignard reagent, RMGX, acts like a carbon anion, so essentially R minus, which again will add to the nitrile carbon. Now this adds only once. That's the new addition right there. And, whoa, what happened here? We went from C triple bond N to C double bond O. We're going to have to talk about that in a second. It has to do something with what happens up here. We can discuss that a little bit. Also, it's slightly related, but even a water molecule, not a terribly strong nucleophile, certainly not as strong as these negative nucleophiles, water can add to the nitrile carbon. You get an idea of where we can make an amide out of that, right? Here's the water oxygen. That's a new oxygen, obviously. That wasn't there before. And then we're going to have to talk a little bit about the transformation that turns an amide into a carboxylic acid. It turns out that this amide is just an intermediate. This is actually not isolated. So all we need is water with acid or base or acid, H3O plus catalyst. And a nitrile turns into a carboxylic acid. Now that's interesting because we talked about how nitriles and carboxylic acids are the same oxidation state. This reaction right here is really the main reason why nitriles are in the carboxylic acid chapter. It's a very useful way of producing carboxylic acids. Okay. So let's start with that. Let's start with a nitrile. Let's add water to it with an acid or base catalyst. We just talked about how we make an amide and then a carboxylic acid. So let's start with the base catalyzed mechanism. None of this should be terribly surprising given what we talked about. If it is base catalyzed, we have a hydroxide ion that will attack the partially positive nitrile carbon, right, exactly as it should. Because carbon can't have 5 bonds, it's going to kick one of these pi bonds up onto the N to make an N minus. This is an imine anion. An imine itself is R N, well, let's draw it like this, R C double bond N with an H, like that. That's an imine. An imine anion is an N minus. But since we have water present, the base is only the catalyst here, we'll have plenty of water present. An N minus is a pretty strong base, so N minus is going to take a proton from water and protonate that imine anion to make just a regular imine. Not so bad, right? In fact, we can draw that. Let's make a water molecule, and I'll make it red, just to match what's in the mechanism there, okay? That is our NH, that is our neutral imine. What happens here? We went straight from an imine to an amide, C double bond O NH2. Yikes, it looks like a lot of stuff happens there, but it's really not that bad because this is a word that should be familiar to us, tautomerization, a word we probably haven't seen since last semester. I don't know. But essentially what's happening here, it's a proton transfer. Take a look at this H right here, which is gone in the amide. This is an NH. This is now an NH2 in the amide. We went from single bond, double bond to double bond, single bond. The general format for tautomerization looks something like this. I'm just going to make X's there. X, X, H. X. So tautomerization happens sort of this 3-atom core right there. We can identify those 3 atoms here. 1, 2, 3. The double bond goes from one end to the other. The H goes from one end to the other. That's tautomerization. Tautomerization happens by essentially a proton transfer. And if it is base catalyzed tautomerization, the OH minus starts the job. Use a different color here. Let's remove, because we're going to have to get rid of this H here, let's start with that. That's going to make an O minus. Draw that right here. RCO minus, still NH. And I got rid of the H there, but we still need to put a new H on over here. Just doing that, just have hydroxide attacking an H made a water for us. So that's helpful. I'm gonna draw it down here because look what happens. O minus is 3 lone pairs. Let's bring one of those lone pairs down. That makes a double bond. Let's use a bouncing arrow to show these pi electrons, creating a new bond that's attached to this N here. And if you look carefully, we should now have a C double bond O. We should now have a C single bond N. We should now have an N with 2 H's. That's the result. Okay? So that's the intermediate of tautomerization. Base catalyzed, acid catalyzed. Just goes in the other order. Acid catalyzed, the H gets added first, and then water removes the extra H. So the steps that we've done just right there have involved the hydroxide ion adding to the nitrile. We just protonate the nitrile and then tautomerize to make an amide. Right there. So that's a mechanism I guess you should be aware of. The thing is, it doesn't stop at that amide. The amide will be able to further hydrolyze. In other words, we're able to add more water to it, and we replace this NH2 with essentially an OH. If it's base catalyzed, it ends up as an O minus right there. That's because the intermediate we get here actually is a carboxylic acid, but we end up with NH2 minus. And NH2 minus is a very strong base. It will just immediately deprotonate the carboxylic acid there. So we're not going to do the mechanism of the amide hydrolysis. We're going to learn that in the next chapter. So that's going to be really similar to a lot of the mechanisms that we'll be doing in the next chapter. So no sense that muddying the water right now for us, but hang on, we'll be doing that next. So in the meantime, though, the acid catalyzed hydrolysis mechanism is pretty similar to this, except when we're doing an acid catalyzed mechanism, usually protonation is the first thing that happens. We saw that with carbonyl compounds. If it's acid catalyzed, the carbonyl will get protonated first. Well, in an acid catalyzed mechanism, the nitrile will get protonated first. We'll end up with something that looks like this. N with 4 bonds, N plus. That now activates this carbon even more for attack by just neutral water, for instance. So I bet you could probably actually figure that out. Let's look at some of the other reactions that nitriles do that we've already mentioned. Instead of having water attack the nitrile carbon, a reactive anion can attack that nitrile carbon. Let's do reduction. LiAlH4, lithium aluminum hydride, is a strong reducing agent. It is essentially, just like we said before, H minus that will attack the nitrile carbon, kick one pair of electrons up onto the N. That makes an N minus. But what's interesting about this is that the aluminum salt that's sort of left over and present along with the rest of the reactive species there, it's a very powerful Lewis acid, so it attaches itself to this N minus and stabilizes that N- really well. Usually if we have an N-, that's really very reactive. That'll just try to react with whatever it can. But that aluminum stabilizes that N- so much, in fact, that another hydride can add to there. And we make, believe it or not, an N2-. We got two aluminums that are able to stabilize that. So just because aluminum has such a stabilizing effect on that nitrogen, that's why we're able to add two equivalents of hydride onto that carbon. And then after the reaction seems like it's done, we just add some water to it as a second step. This is a step 1, step 2 kind of thing there. The workup and quench of the reaction will involve water. That N2- will immediately get protonated by plenty of water, making an amine. So CH2NH2. So that's one way of making an amine. We're going to learn several other ways later on, but this could be useful to us because presumably we could have made a carbon-carbon bond with the nitrile, and reducing it with lithium aluminum hydride is a great way of giving us an amine. It adds this CH2 group also, though. Let's look at what a Grignard reagent does. Grignard reagents add only once. So look at RMgX. That's our Grignard reagent. The carbon is a C-, essentially. It attacks the nitrile carbon, which, like we said, is partial plus. This is our intermediate, an imine anion. The imine anion will be somewhat complexed to the magnesium salt, but that magnesium salt does not stabilize it nearly to the amount that the aluminum salt does. So there's no way another Grignard would be able to come in and add twice to this. That's not going to happen. So the Grignard reagent adds once, where the hydride adds twice. Let's write that right here. Two hydrides adds twice. So what we get is an imine anion, and quenching that with water, we would think we would just get an NH, an imine, but what we actually end up with is a ketone. So let's see if we can figure out why that is. The first thing that you'd think would happen actually does, right? We have a minus, and we're adding water. Usually, we would probably do this with acid. Probably work a little better, or at least an acid, a small amount of acid catalyst is all we really need. The N would get protonated. We'd get a regular imine. NH. One pair, just like that. That's our regular imine. But the thing is, if we have a large excess of water present, and especially if we have an acid catalyst, an imine can turn into a ketone. This is the reverse of what we saw in our carbonyls chapter 19, right? Ketones could turn into an imine, right? If we just had these as reactants, we could make an imine, especially if we removed water from it and had an excess of NH3. On the other hand, if we have an imine with an excess of water, especially if we had an acid catalyst, excess acid catalyst, well, what do we think is going to happen? This is going to be the reverse of the imine forming mechanism from the ketones chapter. I'll give you a hint here. First thing we're going to do is protonate can kind of pretend that was a carbonyl. If we had acid, we would protonate that, right? So let's draw that. That's now an N plus because it has 4 bonds. Can't really do much there, but what that does is activate that carbon for attack by some other kind of nucleophile. What kind of nucleophile are we going to need here? Well, we're going to need a new carbon-oxygen bond at some point. What do we have that would be able to give us a carbon-oxygen bond? We've got plenty of water. I'm going to draw these arrows for you like that. And what I want you to do is see if you can complete that mechanism using sort of what we know about what has to happen, as well as familiar mechanisms before. What we have to end up with is going to look like this. And if I draw it in the direction that we're doing these things, it's going to look like this. R C double bond O. Ketone. So that might be good mechanism drawing practice for you. See if you're able to figure out what happens like that. If you get stuck, take a look at the mechanism for making a ketone into an imine, and the arrows will be different, but all of the intermediates will be exactly the same, going backwards in this one as they were going forwards in that one. So just synthetically, let's look at how this could be useful. If we have a nitrile, we add the Grignard reagent. That, of course, gets added to that carbon there. What we end up with overall is those 2 carbons being added, but a ketone, C double bond O, there as a result. So an excellent way of making ketones. We're going to see some other ways of doing that a little bit later on. But if you're doing synthesis, if you know you need a ketone at some point, if you did a regular Grignard reaction, let's compare with something like benzaldehyde with ethyl Grignard and acid as a workup. What we end up with, I'm having trouble drawing P's there, pH end up with alcohol. Oops, not CH2, CH, and then the ethyl. So, new carbon-carbon bond is right here, new carbon-carbon bond was right there. But the difference between the standard Grignard reaction with a carbonyl is that that just gets kicked up and formed into an alcohol. Grignard reaction with a nitrile, that gets kicked up. We got a double bond there, but that ends up getting hydrolyzed to form the ketone. So, interesting alternative to a Grignard reaction if what we actually need to form is a ketone like that.